More than 100 years have passed since the invention of the first airplane, and it seems that technological progress has brought modern flying machines almost to perfection. But to get to this point, designers often conducted very bold experiments, and the appearance of these experiments, to put it mildly, can be surprising. In the intro to this film, we used footage that for some people looked believable, and for others, not so much. But what in this selection is actually real? And what was simply generated by a neural network? Believe me, it's not that easy to figure it out at first glance. However, by the end of this big documentary, which we've been working on for several months, you will understand the logic and beauty of engineering thought, which throughout the history of aviation has overcome and continues to overcome many obstacles and limitations. And, in the end, the aesthetic pleasure from masculine engineering solutions is guaranteed for you throughout the entire film. Make yourself comfortable. Fastening your seatbelt is not required, but pouring yourself your favorite drink wouldn't hurt. So, let's get started. First, let's take a look at the evolution of this concept. The idea to combine an airplane and a car appeared as early as the beginning of the 20th century. The first aeromobile, the Curtiss autoplane, was invented back in the distant year of 1917, but it never managed to take off in 1937. The American engineer, Waldo Waterman, presented his own version of a hybrid airplane, the Aerobile, which successfully passed flight tests. It could also move on the ground like a regular car, and the wings could be transported in a folded position. Then there was this kind of machine. Just take a look. The propeller is removed, the wings and tail are detached, and you can drive to your beloved grandma. Preparing the machine for driving on the highway or for flight took about 5 minutes. 3 prototypes were built for testing and certification. Over 4 years, they covered a distance of more than 300,000 kilometers, including about 10,000 kilometers on highways. During this time, about 6,000 transitions from one aggregate state of the device to another were performed. In the 50th year, the device received a flight worthiness certificate, becoming the first in aviation history in its class to do so. Then there was the flying conveyor car, and later the more successful model, the Aerocar by Malta Taylor in 1956. But none of these aeromobiles ever managed to go into mass production. The versatility of the design, apparently, turned out to be not so much an advantage as a drawback. After all, each type of transport needs its own infrastructure. Now, when the roads are clearly overloaded with cars and the loss of time in traffic jams has become unbearable, people are once again regularly recalling flying cars. Modern aeromobiles now look like this. The engine, with a power of 140 horsepower, allows it to reach speeds of up to 200 kilometers per hour, as well as cover distances by air of up to 1,000 kilometers. Just 10 years ago, people saw something like this only in movies, but now it's a reality. However, these machines are incredibly expensive, requiring both a driver's and pilot's license to operate. And new concepts of aeromobiles keep appearing, not just as computer renderings, but also as prototypes. Some countries in Europe and the United States of America are promoting government programs for aerotaxi and commercial transportation, hoping that this will help reduce road congestion and occupy a promising niche in business. Therefore, it is possible that in the near future, if not flying sports cars, then at least flying buses and taxis will be soaring above our heads. Now, let's move on to another extravagant idea that was implemented about 70 years ago. The Atomojet, a flying vehicle powered by nuclear fuel. Its reality in the history of aviation looks more like a crazy fantasy. Before the 2 later elements of the nuclear triad appeared, namely ballistic missiles and submarines. In the early years of nuclear weapons development, the emphasis was primarily on the first element of the triad, aviation, since other alternative methods of delivering nuclear bombs were only just beginning to develop at that time. The very first prototype of an aircraft with a nuclear engine appeared in the United States. It was the NB-36, and its development began in 1949 and continued until 1957. This aircraft used a direct flow design. Air entered the engine, passed through the compressor into the nuclear reactor, where it was heated as it passed through numerous holes in the reactor. Then the hot stream of air passed through the turbine and exited the engine through the nozzle. The engine turned out to be compact, only slightly larger than existing jet turbines, but the radioactive air was simply released into the atmosphere, threatening the ecology of its own territories. The Soviet Union began work on its own atomic aircraft in 1955, and the Tu-95 with an additional index was chosen as the test platform. The engineers here took a different approach, using a heat exchange device. Such an engine was less dangerous for the environment, but the heat exchanger was very large and heavy, which made it necessary to create an entirely new aircraft. That was the Tu-119, the development of which began in 1961. They wanted to develop a new nuclear engine for it, but only 2 turbines would be powered by it, while the other 2 would remain on kerosene fuel. In the end, the Tu-119 was never created. Despite the fact that nuclear-powered aircraft were developed in different countries, their design was almost identical. Each side arrived at technical solutions independently. In particular, the cockpits of the aircraft had a lead shell hidden under the fuselage. The engine itself was located in the rear part of the bomb bay and was additionally separated from the crew by lead partitions, but only on the side facing the cockpit. The crew themselves had improved breathing systems, which served as individual protection. But nuclear aircraft were never put into production. After all, by the early 1960s it became clear that aircraft were significantly inferior to 2 other means of delivering nuclear warheads: submarines and ballistic missiles. And after all, airplanes sometimes crash. And the very idea that somewhere a nuclear reactor is flying, which could suddenly crash, became unacceptable. Among the experiments in military aircraft engineering, there were actually many strange machines. For example, the Blyumundfoss by VI-141. This reconnaissance aircraft was produced in Germany during the years of World War II. The main goal of the developers was to place the cockpit so that the pilot would have a convenient view. Despite its unusual shape, test pilots noted good handling. However, the model had a number of other shortcomings and did not go into mass production. Here's another unique aircraft. Imagine how convenient it would be to have your own inflatable airplane that doesn't take up much space, is easy to maintain, and can easily fit in the trunk of a car. In the 1950s, an American company managed, on their second attempt, to bring to life the idea of creating an inflatable airplane, which was named Inflatoplane. The design featured a soft but durable outer skin, while also requiring a rigid connection to the main components of the airplane. The engineers decided to use an advanced composite fabric for that time called AirMet, which is now used in the production of trampolines. Despite the specific manufacturing material, the inflatoplane fully met all the requirements for proper piloting. Such a small, compact airplane could also be useful for military purposes, so it quickly received support and approval from the United States Air Force. The basic design of the inflatable airplane was quickly implemented with minor improvements. Khan passed tests and inspections successfully, but during one of the tests, a terrible tragedy occurred, which slowed down and then completely postponed the launch of mass production for an indefinite period. During another flight, one of the control cables came off, the aircraft's shell tore, and the pilot was struck by the aluminum wingtip. During the fall, the pilot still managed to get out of the cockpit, but he didn't have time to open his parachute and died. This tragedy undermined trust, and the project was shelved for a long time. At that time, there were already 12 ready-to-fly inflatoplanes standing in the hangars, but they never got their turn. Some of the inflatoplanes were sent to gather dust in hangars, while others were given to museums. There is information on the internet that one of the examples can be seen at the Smithsonian Museum in Washington. And here is another interesting piece in the history of aviation. In 1932, Italian engineer Luigi Stipo built one of the most unusual airplanes the sky has ever seen. The airplane, which looked more like a child's drawing than a real flying machine, was named Stipo Caproni, and amazed not only with its size, but also with its appearance. It was built in the shape of a turbine, with the pilot's cockpit located on top, and both the propellers and engines were placed inside the main body. During the tests, despite the ridicule, this tube with wings lifted off the ground and showed good results, demonstrating stability, maneuverability, and a low landing speed. However, Stipo Caproni was unable to achieve the promised results, so the project was shut down and the only prototype of the aircraft was dismantled. Nevertheless, the work of Luigi Stipa and his Wonder airplane made a significant contribution to the development of world aviation and is still being studied in various institutes. It turns out that it was all not in vain. 65 years later, enthusiasts from Australia created a replica of Stipa Caproni, which is now kept in the museum at Toowoomba Airport. And here is something from the same series. The turbine airplane, by the German aircraft designer Alexander Lippisch, was tested in 1972. It was assumed that this drone would be used for reconnaissance. Despite its success, the project was never put into production. The Bundeswehr lost interest in it after deciding to use manned aircraft for reconnaissance. And this goblin also seems to have some kind of family ties with all the previous ones. In 1941, the United States faced the task of creating a long-range bomber that could reach enemy territory and then return after completing its combat mission. At that time, there were no refueling planes, and to solve the problem in 1946, the McDonnell XF-85 Goblin aircraft was created, which could fit inside the B-36 bomber. It was a unique fighter that could be released outside through the bomb bay, and after repelling an attack, it would be caught by a complex mechanism and pulled back into the bomber. The aircraft went through a series of test flights, during which it was discovered that the attachment points were unreliable, and docking with the carrier aircraft was extremely difficult. Because of its shape, it was also nicknamed the egg plane. But after the invention of aerial refueling systems, the need for it disappeared. Here's another awkward dwarf, Snecma S-450. This is an experimental aircraft with vertical takeoff and landing capability, and visually it doesn't look like anything else at all. The project was developed in France, and the first flight took place in 1958. During the test flights, numerous shortcomings were discovered, so in the end the project was closed. And here is something similar. Pogo Conveyor. This experimental vertical takeoff and landing fighter was developed in the 1950s in the United States, to protect ships from air attacks. Thanks to its unusual shape, the fighter took off at a 90-degree angle to the ground. The pilot literally lay in the cockpit head down, and only at an altitude of 150 meters could the plane transition to a horizontal position. Despite the successful tests, the program was shut down. Well, of course, how could we go without this? The legendary VOD VI-173 aircraft, created by the American engineer Charles Zimmerman. It was also called the Flying Pancake because of its unusual appearance. It had excellent flight characteristics and became one of the first aircraft designed for vertical takeoff and landing. Here's another wonder. The Boeing VTOL VZ-2 can be called a mix between an airplane and a helicopter. Its wings rotated, and the aircraft could take off vertically and hover in the air like a helicopter. It was developed in 1957 and delivered to the National Aeronautics and Space Administration Research Center. Another fascinating project that was predicted to be a breakthrough in aviation development was the Russian unidentified flying object. That's what they called the flying vehicle in the West. But its real name was Ecology and Progress, short for Ecology and Progress. The appearance of the aircraft really did resemble a flying saucer. The developer and chief engineer of this project was the outstanding Soviet engineer Lev Shchukin. He worked on his creation for many years. And in 1994, on the territory of the Saratov Aviation plant, the first crew tests finally took place. Eyewitnesses say it was an amazing sight. Uninformed people could really think that the aliens got tired of hiding and boldly flew straight to Saratov. Jokes aside, the Russian unidentified flying object performed excellently during the tests and made the entire engineering world pay attention to it. According to experts, This aircraft was decades ahead of aviation development. It didn't need airfields at all. It could land anywhere, even on a lawn or a swamp. Moreover, the craft's features were remarkable, capable of reaching altitudes over 6.21 miles and speeds of around 372 miles mph. Such an aircraft could be useful anywhere, from passenger transportation to rescue operations. But then the turbulent 90s and the period of restructuring intervened. Interestingly, the development of the crew was listed as a separate line in the state budget, but sufficient funding for Lev Shchukin's ambitious project never arrived. The engineer tried to find the money on his own, but in 2001 he suddenly died of a heart attack. The project was frozen, and the Russian unidentified flying object was sent to the Military Technical Museum in Chernogolovka near Moscow. Here's another amazing Soviet development: an experimental ekranoplan developed at the Alexeyev Design Bureau called the Korabl Maket, or Korabl Maket for short. More often, this abbreviation was deciphered as the Caspian Monster. The wingspan was 37 meters, and the length was 92 meters. For 15 years, this aircraft was tested, but in 1980, it crashed due to pilot error. There were no casualties, but they never restored the Caspian Monster. Here's another monster. The vertically taking off amphibian, or simply the VVA-14, designed by the Soviet engineer-emigrant Roberto Bartini, combined the functions of a seaplane, a bomber, and a torpedo carrier. This aircraft was created in 1972 with the purpose of detecting submarines both from the air and on the water. The aircraft possessed characteristics that are impressive even by today's standards, not to mention during the Cold War era, and amazed people with its versatility. The VVA-14 was designed to land vertically on water, sand, snow, or swamps. It was armed with numerous aerial bombs, mines, and torpedoes. The amphibious aircraft could fly right above the water, which made it undetectable by radar. But the appearance of this monster left much to be desired. Apparently, this bothered the eccentric Roberto Bartini the least. During the tests, the VVA-14 performed well, but the aircraft never entered mass production. Bartini passed away, the engineers faced technical problems and insufficient funding, and the project was abandoned. In the long run, the Soviet amphibious aircraft VVA-14 could have become the most advanced weapon of its time, with no analogues in the world. However, its fate ended in the Central Air Force Museum in Monino. The United States also had unconventional designs that tried to combine air and water. For example, the V-2 was an experimental American supersonic fighter that could glide, meaning it could use water for takeoff and landing. American aviation has created unique aircraft like the legendary Blackbird SER-71. This American strategic supersonic reconnaissance aircraft looks so modern that it's hard to believe it first entered service back in 1966. The aircraft was retired from United States service 32 years later, in 1998. During the Cold War, the SR-71 repeatedly violated the airspace of Russia and Cuba for reconnaissance purposes. At supersonic speeds, the aircraft would heat up so much that special suits were developed for the pilots, which were later used by shuttle astronauts. It's interesting to look at this aircraft in connection with the recent Tom Cruise film, Top Gun: Maverick. Does a hypersonic aircraft like the one shown in the film actually exist in reality? Actually, although the aircraft was created exclusively for the film, it was designed by the same legendary engineering bureau of the corporation that developed not only the Strategic Reconnaissance, 71, but also such famous aircraft as the U-2, F-117, and F-22. The SR-71 had a maximum speed of 3.3 Mach, which of course is far from the 10 Mach shown in Tom Cruise's film. And finishing with movie bloopers, it's worth noting that in the film, the aircraft reaches a speed of 9 Mach quite calmly, and only the final step to 10 Mach becomes a problem, as evidenced by the heating of its skin. In reality, heat accumulation occurs at much lower speeds. The The skin of the X-15 experimental aircraft from the 1960s, which to this day holds the record for the fastest manned flight, reached a temperature of 650 degrees Celsius at a maximum speed of 6.7 Mach. For reference, iron starts to glow at 460 degrees Celsius and titanium at 455 degrees Celsius. One might assume that the skin of the hypothetical aircraft is made of something more heat-resistant, but in any case, the problem of the body heating up would have appeared much earlier. Now let's take a look at developments that are historically connected to National Aeronautics and Space Administration, the flying bathtub. National Aeronautics and Space Administration needed wingless aircraft because they wanted to create a controllable capsule for returning astronauts to Earth. The optimal shape for such shuttles was found to be an irregular cone. Externally, the vehicles looked like bathtubs. 5 National Aeronautics and Space Administration projects were created, which were similar to each other. Over 3 years of testing, more than 400 launches of the vehicles from Earth were carried out, as well as about 80 flights behind airplanes. However, with the start of the shuttle project, the need for such strange mini-shuttles disappeared. And this is Pregnant Guppy. The airplane also appeared to meet the needs of the United States space program. National Aeronautics and Space Administration required a vessel for the construction of the spaceport at Cape Canaveral, and for delivering rocket parts there. They didn't fit into regular airplanes. The project for a more spacious transport aircraft was assigned to Boeing. That's how the aircraft 377 PG, also known as Tri-77 or Pregnant Guppy, originated. The payload capacity of the new aircraft reached up to 26 tons. The development of the Pregnant Guppy project was undertaken by the manufacturer for their own needs, to transport aircraft parts from one factory to another. With a full load of 47 tons, the flight range reaches about 1,700 kilometers. With a half load of 26 tons, the flight range increases to 4,600 kilometers. There are a total of 11 production facilities across Europe, but the assembly itself takes place in Toulouse and Hamburg. That's why, to make the process cheaper and simpler, it was decided to create their own fleet of cargo planes. Since January 2020, a new modification has been flying in the sky. Next in line is McDonnell Douglas X-15. The X-15 is an American experimental rocket plane with a rocket engine. It was the first piloted hypersonic aircraft that managed to carry out manned suborbital space flights back in the 1950s. In 1963, the X-15 managed to reach an altitude of 66 miles and achieved a speed of 170 miles per hour. One of the test pilots of the rocket plane was the legendary Neil Armstrong. Here's another marvel from National Aeronautics and Space Administration. National Aeronautics and Space Administration is research aircraft for studying variable wing geometry. This was the world's first aircraft with a swept wing compared to a wing with symmetrically variable sweep. This design has 11 to 20% less drag, 14% less mass, and 26% less wave resistance. The aircraft was built in 1979 and made its first flight on December 29th of the same year. The tests were conducted until the beginning of 1982, and during this time, 17 pilots mastered the AD-1. After the program ended, the aircraft was placed in the San Carlos Museum, where it remains today. And this unusual craft is also connected with space prospects. The American carrier aircraft, designed to launch spacecraft, is the largest in the history of aviation. It looks so fantastic that it's hard to believe it actually exists. The twin fuselage design is joined by the longest wing currently in existence. Its wingspan is 117 meters. The plane has its own name, Roc, after the giant bird from Eastern legends that was capable of carrying an elephant in its claws. In May 2017, the company rolled its creation out of the hangar. 2 fuselages connected by a massive wing, 6 engines, and 28 wheels. The model was created with a simple and clear goal. The aircraft should ascend to an altitude of about 10 kilometers and launch space rockets. At that moment, The rocket activates its engines and delivers the satellites it carries into space. One of the main investors in the project was Paul Allen, a billionaire and co-founder of the corporation. At first, the project was considered ambitious and even attracted the attention of Elon Musk, but in the end, he focused on his own developments. A large number of technical nuances and the lack of potential buyers led to the project being put on hold. And the death of the main investor, Paul Allen, in 2018 cast even more doubt on the future of this giant. During all this time, this giant aircraft carrier has made only 2 flights. However, recently there have been more and more rumors that the craft will be used for testing United States hypersonic weapons. Speaking of the present, some aviation engineers are betting on electric airplanes. They allow flights to be much cheaper. Less than a year ago, an electric airplane built from scratch in Israel made its first flight. The developers promise that it will begin making its first commercial flights in just 5 years. But you can't fly very far on such a plane. The maximum distance it can cover: 500 kilometers. And it can carry only 10 people. The Swedish electric plane ES can carry 19 passengers, which is twice as many, but its range is even less, only 400 kilometers. Electric aviation's speed averages only 217 miles per hour, which is not impressive. The problems all come down to one thing: the batteries. So, it turns out that in the near future, electric jets are unlikely to move much faster than cars. Not so great, the airplane of the future. So, what should we fly on then? Major manufacturers are considering hydrogen. Here is the Zero-E project from one of the world's largest aircraft manufacturers. According to French developers, the hydrogen-powered aircraft of the future with zero carbon emissions will look like this. The same airliner in 3 different versions: classic, turboprop, and futuristic concepts. The last aircraft, a flying wing type, has never been built in civil aviation before. Hydrogen is fuel. It's cheaper, which means ticket prices should go down. But hydrogen tanks take up a lot of space on board. And because of them, the aircraft will be able to carry far fewer passengers. So there are still a lot of questions here. Engineers from the Netherlands agree that the future lies in a new form factor. Their design is similar to the American concept. But this plane will fly on traditional aviation kerosene. This will save space and increase passenger capacity by almost 1.5 times. With the same size as the French one, the plane will be able to carry 320 passengers. It turns out it will be able to compete with modern wide-body aircraft, because with similar characteristics, it will need 20% less fuel. And such savings are achieved only by changing the aerodynamics of the airliner. All that remains is to construct such an aircraft in the real world. Engineers have only gotten a radio-controlled model airborne so far. Speaking of models, by the way, there are unusual events like this one, a meeting of aviation model enthusiasts in Germany. Here, replicas of all kinds of legendary Soviet Il-62s and more are flown. Even though this seems like a hobby, some models require a whole team to operate. And such toy airplanes can cost up to 10 million, if we're talking rubles. Most likely, the men who are into this had aviation modeling clubs as kids. And some part of those childhood emotions is still alive in their hearts. All of this, including radio-controlled models, is nice and beautiful. But after seeing such a variety of devices capable of moving through the sky, you start to wonder, can engineering thought surprise us not only with the external features of this or that concept, but also with its inner content? The very thing without which any airplane is just a museum model? Look at this monster. This is the gigantic aviation engine Ultrafan, with a power of 87,000 horsepower from Rolls-Royce. Its diameter is more than 3.5 meters. Ultrafan will run exclusively on environmentally friendly aviation fuel, sustainable aviation fuel. Ultrafan testing will start right at the beginning of the year 2023. And, as they say, a big engine needs a big test stand. More precisely, the biggest one in the world. The site with Test Bed 80 was launched 2 years ago and was created specifically with the aim of refining the UltraFan. And just recently, they brought in the so-called demonstrator, which was created specifically for this giant. Probably every viewer of this video has flown on an airplane, but hardly any of you can actually imagine how the engine of this machine works. What's inside? A fan? A turbine? Or maybe a couple thousand little gnomes who are spinning special pedals? Let's figure it out. At the dawn of aircraft construction, piston engines ruled the scene. Now, they've almost become a thing of the past. Although, how do you say, "nice to meet you"? This is Solera 132 gallons, a prototype of a single-engine piston aircraft. In shape, the aircraft resembles an egg with wings and looks like a children's toy, but its capabilities are quite serious. By using an unusual shape, the engineers reduced aerodynamic drag by 59%. Not bad for a toy. This is Solera's closest competitor. Let's compare the technical specifications of the devices. The cruising speed of Solera is 740 kilometers per hour, and the flight range is 8,300 kilometers. The cruising speed of Business Jetta is 842 kilometers per hour, and the flight range is 11,519 kilometers. It seems pretty close, but for every 100 kilometers, Boeing uses 258 liters of fuel, while Solera uses only 13. It turns out that this funny plane is more economical than a sport utility vehicle in city traffic. And if the pilot wants to save even more fuel, he can simply turn off the engine. With the engine off, Solera can glide for a distance of more than 200 kilometers. There are other examples of engineering ingenuity from modern times. The related thing would be an outdated propeller. This is the world's first 11-blade propeller. It successfully completed its first test flight, as reported in a press release by its developer, MT Propeller. This is another achievement for the company, which previously produced 5, 7, and 9-blade propellers. The group of developers recorded a 15% increase in the static thrust of the new propeller compared to the 5-blade propellers from the same company. The aircraft's propeller system, combined with a low revolutions per minute power source, can open up new possibilities for productivity, efficiency, and low noise levels. After all, even an electric motor can serve as a low revolutions per minute power source. However, despite all these exceptions to the rule, it is still not piston engines with propellers that dominate today, but two other types. The most popular engine installed on modern civil aircraft is the turbofan. Its advantage is that it is quite compact. The airflow in it moves along two circuits. In the inner circuit, the air is compressed by the compressor, ignited, spins the turbine, and is expelled through the nozzle, creating thrust. The second circuit starts with the large fan that we see on the outside. The fan drives and moves air through the circuit, creating additional thrust and increasing the engine's efficiency. Let's describe this scheme using the example of the PD-14 engine, a fifth-generation engine. Don't confuse the fifth generation of engines with the fifth generation of fighter jets. Engines from the World War II era could heat up to 900 degrees, and this benchmark for the fifth generation has actually doubled. At the same time, the ability to operate in this mode for an extended period has also increased. In the front part is the compressor, whose task is to compress the air passing through it. The air is pushed forward by stages of rotating disc-shaped structures of complex form with blades around the circumference. In essence, they are fans. There are a total of 11 of them here, 3 low pressure and 8 high pressure. Moreover, as the air moves through the engine, the number of blades increases, while the volume through which the air passes decreases. So, the air from a cool breeze turns into a hot gas, with its pressure increasing 40 times. Next after the compressor comes the culprit of the fiery show, the low-emission combustion chamber, where fuel is injected and ignited, heating it up to almost 2,000 degrees. The chamber itself is a work of art. The design features a very clever flow configuration, including 48 injectors, and is so complex to manufacture that its parts are printed from metal using 3D printers. And this is not just a tribute to industrial fashion. Otherwise, it's simply impossible to make such a mechanism with the specified parameters of compactness and reliability. In the turbine, the process is, in a sense, the reverse of the process that occurs in the compressor. Now, the heated compressed air rushes through the mechanism, first hitting 2 stages of high pressure, and then 6 stages of low pressure. Now the gas itself rotates the stages, and part of its energy is transferred through the turbine to the shaft, which drives the fans and the compressor stages that, in turn, compressed and pushed the gas here. That's the cycle of energy in the engine. The hot gas that has passed through the turbine bursts out with a roar through the nozzle, creating thrust. The main challenge for engineers in the hot section is the structural elements that come into direct contact with the working area, primarily the blades. They must be able to withstand enormous loads without melting or breaking apart. There are several solutions to this problem. First, specially created heat-resistant alloys. Second, inside these housings there are special channels through which air passes, cooling them from the inside. As a final touch, special ceramic coatings are used, which take the first impact of the heat. These solutions, in various combinations, allow the blades to operate normally. The outer contour is simpler. There is no combustion chamber, no turbine, and only one fan. But what a fan it is! It is made of hollow titanium blades. Unlike conventional metal blades, which can be seen on most aircraft engines, the new blades are lighter, larger, have a complex aerodynamic shape, and do not require additional reinforcing elements. Steel bats are still slightly heavier than composite ones, but balance is a key factor to consider. Composite blades are quite complex and expensive to manufacture, and the advantage of their weight becomes decisive as their size increases. Composite fans are not installed on small engines, so you end up with the same thing for a higher price. And, on the contrary, on large engines, composite fans are practically the only viable option. Metal would be too heavy here. Now, we are about to encounter a labyrinth of units, cables, pipes, pumps, and sensors that surround the engine along its outer contour. Usually, people don't talk much about them because just try to figure out what all of this is. But without all of this, any aircraft engine is just an art object. The engine's component base is almost entirely Russian. There are only 4 countries in the world capable of creating modern turbofan engines through a full production cycle: the United States of America, the United Kingdom, France, and Russia. Each of them strictly protects the results of their research and their know-how in engine manufacturing. France produces the hot sections of engines 1, 4, and 6 solely on its own territory. Such units are designed over years. A modern aircraft engine takes 1.5 to 2 times longer to develop than the aircraft itself. For example, the PD-14 began development in 2008. The designers implemented 16 key technologies which cannot be mastered without creating their own production facilities. The second type of engine is the turbojet. This type of engine is quite bulky and, as a rule, is used on military aircraft of various classes. For its installation, either part of the fuselage of the carrier aircraft is used, or special recesses are made along the sides of the fuselage. The turbojet engine has high power, and, as a result, helps the aircraft reach high speeds, up to and including supersonic speeds. In a turbojet engine, air is sucked into the compressor, which is driven by the external cold turbine, and after compression, it is supplied to the hot turbine. This engine is not economical at all, and therefore it is very rarely used in civil aviation. However, this has happened in history. The most obvious examples of using turbojet engines on civil aircraft are the Supersonic Concorde and Tu-144. Let's take a closer look at them. For the first time, the development of the supersonic aircraft Tu-144 became known in 1962. It was positioned as a direct response to the foreign Concorde, which was supposed to become the first passenger aircraft to break the sound barrier. However, the first flight of the aircraft from the Tupolev Design Bureau took place on December 31, 1968, 2 months earlier than the flight of the Concorde. The supersonic aircraft Tu-144 and Concorde are commonly considered twins. Some people are convinced that the aircraft have many similarities because one side stole the blueprints from the other. But in reality, engineers from the Soviet Union, Great Britain, and France often met and discussed their ideas. There are similarities, and very significant ones, but at the same time, the aircraft also have serious differences. The main differences are as follows. The Tu-144 has canards in the nose section, while the Concorde does not. The Tu-144 was made from large sections of solid plates, while the Concorde was made from small parts joined together with rivets. The Tu-144 was equipped with the NK-144 jet engine, while the Concorde had the Olympus 593 engine. However, the fate of these two aircraft is very similar. Supersonic passenger planes were taken out of service due to a series of accidents. For the first time, the Soviet Tu-144 aircraft crashed in 1973 during the air show in Le Bourget. 6 crew members and 8 people on the ground were killed. The second time, the aircraft crashed in 1978 during a test flight, resulting in the deaths of 2 flight engineers. The third emergency incident occurred in 1980 when, during testing, one of the engines on the prototype failed. The crew regained control, landed the aircraft, and survived. In 1981, the aircraft was about to begin commercial flights, but a fire broke out on board, and the crew had to evacuate the aircraft through the emergency exits. After all this, interest in the aircraft disappeared, but later it was sometimes used for urgent cargo and mail flights between Moscow and Khabarovsk. The last flight was made in 1999. The Concorde aircraft got into trouble much less often than its Soviet counterpart, but the disaster that occurred in Paris in the year 2000 turned out to be the most tragic. During takeoff from Paris to New York, the left landing gear of the Concorde ran over a piece of another aircraft's fuselage, which resulted in a fire. The disaster claimed the lives not only of all 100 passengers and 9 crew members of the aircraft, but also of 4 people who were in the hotel. After this terrible event, they tried to continue using the aircraft, but after several more malfunctions, the project was shut down. But even if we don't talk about supersonic airplanes, is it really impossible to just make a regular airplane fly faster? Yes, it's possible, and they are capable of reaching those very 800 to 559 miles per hour, which often become the cruising speed of regular airliners. But there's just no point in doing that. The costs will increase significantly, while the travel time will be reduced by literally just 10 minutes, especially if the flight isn't a long one. There is another question that might interest a typical airline passenger. Why don't airplane engines stall during rain? And how dangerous is it to fly in a downpour? Most car enthusiasts know that water should never get into the engine under any circumstances. Moisture in an internal combustion engine leads to fatal consequences, from broken parts to the engine bursting. But airliners fly using engines that convert the thermal energy of fuel. Accordingly, there should also be no water in their engines. However, there is no moisture protection system in aircraft engines. Planes don't even have bird screens installed in front of the engines. So how do airliners fly in the rain? Why doesn't water harm their engines? Indeed, an airliner can fly even in heavy rain. At this time, every cubic meter of air contains about 10 cubic centimeters of water. The aircraft engines take in huge masses of air. As a result, on average, about 1 liter of water enters the engine every second. In just a few minutes, a significant amount of liquid should accumulate. But why doesn't it stall the engine or cause it to fail? First of all, the airflow in airplane engines is distributed at a ratio of 1 to 10. Most of it doesn't go into the engine itself, but rather to the outer bypass. 90% of the air passes through it, increasing thrust. Some of this also works as cooling. The air is captured by something like a fan. It acts as a centrifuge. Under its influence, the heavier water particles end up near the walls of the outer bypass, while the lighter air stays in the center. Next, the air masses enter the compressor. As a result of compression, the gases are heated up to 260 degrees. Accordingly, The water evaporates even before it actually enters the engine. The second reason why water does not harm the airplane engine is the size of the engines. That 1 liter of liquid per second that could potentially get into the engine is negligible on its scale. Modern airliners are tested for safety, and it is ensured even with 75 liters of water per second, which is impossible in the sky even during the heaviest downpour. A much greater threat to an airliner can be posed by hail, because solid particles will hit the fuselage and engine at bullet speed and will behave very differently from water. But this atmospheric phenomenon is much rarer and more predictable. And almost always, airliners manage to avoid the hail zone. And here's another interesting question, by the way. Why did they stop making such beauty? Why don't they install engines inside the airplane wings? The first commercial airliner in history to be equipped with 4 engine installations mounted inside the wings was the British. DH-106 made its first flight back in 1949 and already in 1955. The Soviet Tu-104, with engines built into the wings, took to the air, and a similar design was also used in the Tu-124. So why was the decision ultimately made to abandon this design when at first glance it seems to have an undeniable advantage? The first and perhaps main advantage of engines in the wings is an aerodynamically clean wing, which in turn allows for significantly greater lift. And for the first jet airliners, this was indeed a critically important factor. After all, if we look at the Comet, for example, it was originally equipped with Rolls-Royce engine installations with a thrust of 32.7 kilonewtons, which is incredibly little. But if we look at the Rolls-Royce engines with a thrust of 7,000 at 324 kilonewtons, the difference is obvious. The advantage of built-in engines with a 324 kilonewton thrust is clear. Also, an advantage of built-in engines was a lower yawing moment in case of engine failure. Yes, nowadays modern engines break down extremely rarely. Statistics show 1 failure per 100,000 flight hours. But back in those days, a good indicator was considered to be 1 failure per 2,500 flight hours. That means, back then, engines failed almost 40 times more often. The third advantage is a lower tendency to ingest debris compared to engines mounted under the aircraft wing. But this configuration also had its drawbacks. So, if there was a fuel leak and, as a result, an engine fire, there was a high probability that the wing itself would be damaged, as well as the neighboring engine, if we consider the Comet specifically. But an engine suspended under the wing is quite well isolated and, in fact, can even burn out completely without causing significant damage to the airliner as a whole. In addition, an engine mounted higher is simply harder to service because of its higher position. Another significant drawback is the inability to upgrade the engines without major structural changes. After all, when replacing a built-in engine, it was inevitably necessary to adjust the wing geometry. And that's far from a cheap undertaking. In this regard, the 737-7 is a true example of rational economy. This airliner has been produced for 54 years now, and during this time it has undergone 4 major modifications with engine replacements, while the fuselage itself has changed only slightly. In addition, the advantages of placing the engine under the wing include these factors: more space in the wings for fuel. At the same time, if the fuel supply system fails, the fuel will flow to the engines by gravity. In addition, the suspended engines also help balance the wings themselves, damping unwanted vibrations, which also allowed for lower strength requirements for the wings and, therefore, made them lighter. These advantages determined the appearance of modern airliners, while engines inside the wing were relevant only at the very dawn of civil aviation. In today's reality, flying on airplanes with such a configuration would be too expensive and impractical. Well, how about safety in that case? Most likely, every first-time passenger asks themselves this question when they take their seat according to their purchased ticket. Do airlines try to save money on parachutes? And what's the situation with this in aviation nowadays? Take a look at this. On the show Mythbusters, they shoot a 2-gram ping-pong ball straight through a paddle. And this photo is also related to fast-moving objects. This is the trail left by a bird that was lucky enough to add its own speed to the speed of a fighter jet. A 2-kilogram seagull can leave holes in the fuselage comparable to those made by a shell. Here are a few more shots that will add fuel to the fire of your aerophobia. Or here's another one. At the American University in Dayton's laboratory, a drone was accelerated to nearly 400 kilometers per hour. They showed what would happen if it crashed into an airplane. The plastic drone enters the metal wing like a knife into butter. It's not hard to imagine what would happen if the speed were higher and the drone heavier. Fortunately, birds and drones only meet at low altitudes. They simply don't reach the cruising altitude of large airplanes. Around airports, birds are deliberately scared away. They put up scarecrows, launch kites shaped like birds of prey, use real hunting birds of prey, or simply shoot at the birds. In busy airports, ultrasonic repellers work best. For the same reason, many global positioning system drone firmwares include zones where the drone cannot take off. Most often, these are located near airports. Despite these safety measures, no new aircraft model will be released for mass production without conducting special tests for collisions with birds or other foreign objects. Especially for such tests, a real chicken cannon was created. And this is not a joke. Despite all the more advanced technologies, birds still pose quite a significant danger. Engineers with serious faces actually load the cannon with chicken carcasses weighing about 2 kilograms and shoot them at the aircraft's fuselage, windshield, and engines at a speed of about 540 kilometers per hour. According to statistics, birds collide with airplanes more than 5,000 times a year. Over the last quarter of a century, they have put 160 aircraft out of commission. The largest disaster caused by birds happened in 1960. At that time, 62 people died. Fortunately, most such aviation incidents occur without casualties, but not without nerves. A few years ago, a flock of seagulls got in the way of a Moscow Simferopol flight. The birds were sucked into the engine air intakes. The left engine stalled immediately, and the right one lost thrust. Right ahead, there was a large field. The soft soil and tall corn cushioned the hard landing. This is one of those cases when the pilot's skill saved the passengers' lives. After all, an ordinary person often thinks that if a plane loses its engines, it's best to land on water rather than on solid ground. It seems like water should soften the impact, but that's not the case. The speed of the airliner at the moment of landing is about 250 to 167.77 miles per hour. The impact with water in this case is practically no different from hitting the ground. During a water landing, the aircraft can break apart. If you raise the nose too much, there's a risk of the tail hitting the surface of the water, and then the tail assembly could break off. On the other hand, the engines could scoop up water, and as a result they might break off, or the plane itself could sink. It turns out that in this case, there will be problems not only for those passengers who can't fly, but also for those who can't swim. And still, maybe not as much is being done for flight safety as we would like. Maybe greedy capitalists are still stingy with money for tests or for the safety system. After all, in an extreme case, they could have handed out parachutes to every passenger. Let's see what's being done in this area. To understand a car's safety margin, crash tests are conducted. But for airplanes, this is rare. All emergencies are usually simulated in the laboratory. Although sometimes airliners do get crashed. For example, this decommissioned one. F-28. There are 24 mannequins on board. Men, women, children. The altitude is 45 meters. It's a real hard landing. Here are more famous shots from the crash test of the 727th Boeing. This video is part of tests conducted to visually determine the most dangerous seats for passengers on an airplane, as well as to find out the impact of seatbelts on the preservation of life and health. The organizers of the experiment simulated not a plane crash, but an emergency landing. It turned out that the mannequin with the seatbelt fastened, positioned in the emergency pose, was almost unharmed. The mannequin that remained sitting upright suffered a head injury, and the unbelted one died. And in these frames, you can see the results of tests that aim to determine the maximum bank angle for passenger airliners. Look, a 254-ton airplane took off at a 90-degree angle, almost like a fighter jet. Many people are familiar with the shaking of an airplane in flight due to turbulence. When building airliners, tests of this kind are always conducted. If the wings of an aircraft remained immobile, they would fall apart during turbulence. That's why the wings of modern passenger airplanes are very flexible. Each wing can easily withstand a load 1.5 times greater than what it experiences during flights in any conditions. And the wing's flex can reach up to 5 meters. Moreover, the final test includes breaking the wings off. Yes, it's expensive, but it helps determine their strength limit and guarantees that it far exceeds the predicted load level. In short, it's all to make sure that the wings definitely won't break off during flight. All this is good, but there's another interesting question related to safety. Can hackers hack an airplane? A few years ago, the United States Department of Homeland Security commissioned an experiment, asking a group of experts to hack the control system of a Boeing 757, which was allocated specifically for this purpose. It took the team only 2 days, and they used only equipment that could easily be brought through airport terminals. Moreover, the hackers did not involve any insiders from the crew and didn't even touch the Boeing itself. Only radio communication, only hardcore. What exactly they did, of course, is not disclosed. The vulnerability was not news to the aircraft designers, unlike the pilots who were present at the announcement of the experiment's results. It is believed that the new models are protected from the discovered vulnerability, but in the old ones, no one has fixed anything. Smaller companies that mainly operate old Boeings are unlikely to deal with this, considering that such aircraft firmware updates are extremely expensive. Lightning events. Such stress tests also exist, because on average every commercial airplane is struck by lightning about once a year. Engineers even have a special generator that creates lightning under artificial conditions and then strikes the airplane in the required spot. Nevertheless, despite all these tests and the minimal chance, about 1 in 3 billion, it's still impossible to guarantee 100% flight safety. That's why various proposals regularly appear. For example, to turn the passenger cabin into a rescue capsule. In case of an emergency, it separates on parachutes. But this only works in theory. First of all, this design would be very expensive. And secondly, even if such things were built, they would save the lives of only a very small number of passengers. Why? It's assumed that a detachable passenger cabin would be useful if the engine fails. But that's exactly what has happened very rarely over the past 10 years. Such malfunctions have caused less than 3% of all fatal accidents. Things are much worse during takeoff and landing, when a detachable passenger cabin is useless. Moreover, when the plane is taking off or landing, it is usually near a populated area. And now imagine what the consequences would be if the cabin with passengers fell on some house. However, the idea itself is not bad, and actually works with some limitations in general aviation. Just take a look at these shots. These are examples of how a parachute system saves the lives of pilots and passengers of small aircraft. With larger aircraft, first of all, it's not cost-effective, and secondly, at their speeds, using a parachute would lead to even worse consequences. Therefore, it is considered that it's easier to land even outside an airfield, in a field, or even on a river, than to use a parachute system. Naturally, the most common and logical question any passenger has after seeing such footage is, where is my personal parachute? Remember that joke? During a night flight, when all the passengers are asleep, the captain sneaks between the seats with a parachute on his back. And when a waking passenger asks, "What's going on?" he replies, "Go back to sleep, everything is fine. I just have some trouble at work." Jokes aside, if I answer briefly, you can't count on a personal parachute. But if I elaborate, here's what it's all about. First of all, if an airliner were to carry parachutes for all passengers and crew, that would be tons of extra weight, which means less luggage for people and ticket prices that are astronomical. Another point is that a parachute can only be used at certain speeds. For example, for a standard military parachute, that's no more than 400 kilometers per hour. And most airliners fly at an average speed of 800 kilometers per hour. If you jump out at that speed and open the parachute right away, it will simply tear apart. Basically, you can jump out and free fall until your horizontal speed drops below 400 kilometers per hour. But only an experienced parachutist can do that. For a beginner, that's an extreme load. Besides, it's not that easy to know when your speed has dropped enough. The route of a standard airliner goes at altitudes of 10 to 12 kilometers, and decompression or opening the doors at such an altitude will cause at least loss of consciousness for all passengers in the cabin without oxygen masks, and possibly even death. You need oxygen tanks and special helmets. And you should look about the same as an Imperial stormtrooper in full gear. Not comfortably sit in a t-shirt waiting to arrive at your favorite Turkish hotel. And in general, what is flight safety? Literally, the term flight safety sounds as follows. Flight safety is the condition of an aviation system or organization in which the risks associated with aviation activities related to the operation of aircraft are reduced to an acceptable level and are controlled. In other words, a certain percentage of casualties is implied, but this percentage must be kept to an absolute minimum, and all risks associated with aviation activities must be controlled and ideally reduced to zero. 15 years ago, this meant that for every 1.2 million passengers transported, no more than one passenger was lost. If you set the bar lower, you can reduce the cost of flights, but at the same time, safety is compromised. If you set it higher, you can achieve better passenger survival with incredibly complex measures, but the ticket price will be significantly higher. So this is an optimization problem where you need to find the flight conditions that are safe enough. But at the same time, it shouldn't cost $200,000 for a one-way ticket. In terms of safety, civil aviation ranks first among all means of transportation. Trains are considered the second safest for passengers. At the same time, nobody is afraid of trains, but many people are afraid to fly on airplanes. We have two pieces of news for you, one bad and one good. First, the bad news. The fact is, if something globally goes wrong and the plane starts to fall, it will crash no matter what. After all, these things are made to fly, not to fall and stay intact. No matter what the engineers do, this can't be avoided. So basically, no one even tries to keep the plane's body intact in case of a crash. Now, people are more concerned with making airplanes lighter, more aerodynamic, and more resistant to wear. Special attention is given to composite materials. They can reduce weight by 20%. Moreover, humanity has already gone through something similar. In the days of the Wright brothers, airplanes were made from sticks and cloth. That is, from wood and fabric. Then, for more than 60 years, they were made from aluminum until people figured out composite materials. They were first introduced in the construction of military aircraft in the 1960s, but, as is usually the case, everything gradually transitioned from the military industry to civil aviation. For example, in the 777, which has been produced since 1993, composites made up 12%. But in the 787, which has been flying since 2011, composites already make up about 50%. At the same time, in the 350, which was introduced in 2015, composites already make up 53%. But it must be admitted that no matter how amazing composite materials are, they have their own drawbacks. Yes, they are lightweight, but detecting damage in a fuselage made from such materials is much more difficult than if it were made from metal. And this can be critically important. On April 28, 1988, an Aloha Airlines plane took off from Hilo to Honolulu at an altitude of 328 yards. A section of the plane's roof suddenly tore off. There was an explosion, decompression, and one of the flight attendants was simply blown out of the plane. Another 8 people were seriously injured. However, the plane managed to land. What was the cause of the accident? It is believed that so-called metal fatigue was to blame. One of the passengers later said that she noticed a crack in the fuselage when she was boarding, but she didn't tell anyone about it. Could the crack have caused the plane crash? Quite possibly. Now engineers have equipment that can help assess when the metal has fatigued and detect such cracks. But in the case of composite materials, finding such damage is significantly more difficult, which means the risk of similar incidents may increase. Let's conclude on an optimistic note. Don't be afraid of flying. Historically, every plane that took off has always returned to Earth. In the end, even in the show Kalambur, which your parents loved, in the cool epic storyline, they still landed. In the latest episode, we're waiting for your fresh or old jokes on the topic of the video in the comments. It'll be interesting to read them. Thank you for watching and see you in future episodes on our channel.